Hi everyone! Today our goal is to be able to calculate the work done by a force on an object and to be able to calculate kinetic energy and apply the work energy theorem. So the work in physics is very different from the work we use in everyday life. The definition of work in physics is very specific, and it is a process of moving an object by applying a force. Work is a scalar quantity and it's measured in joules. 1 joule equals to 1 Newton multiplied by 1 meter. So the formula for work equals the F, the parallel component of the force multiplied by the displacement, or the force multiplied by the displacement d and by the angle, by the cosine of angle between those two. Work is only done when the force and displacement are in the same or in opposite direction, which means that if the force is at an angle, we have to take the component of the force along the displacement. So another way to remember what work is to think about this statement, that work is done by something on something else. And now stop and think. Here's the question: how much work is done by a man who applies 100 newtons of force to a car that does not move? So think about it, then continue, pause it and continue the video. So to solve this problem, it's a man pushing on the car, and we know the force is 1000 newtons, distance is 5 meters, that the car moves 5 meters to the right. So the work is force times distance, 1000 times 5 meters, it's a 5000 joules. All right. Now we're asked, what is the work that the friction force is doing? So let's look at this again. We have a man and a car pushing to the right. So this is, the dot is the car. So the forces that are acting on the car are the F of push. The man is pushing on the car, and the friction between the road and the car is the opposite direction of to the motion. So the net force is going to be equal to the F push minus F friction. So we can find that F friction is going to be equal to 200 newtons, which is 1000 minus 800. And if we know the force of friction, we can find the work the friction does. But here we have to be careful. We have to put the angle between the force and the displacement. So the general formula is the force times displacement times the cosine between those two. So in the first direction, we just use the force times displacement because they're in the same direction. In this situation, they're in opposite directions. So the cosine theta is going to be 180 degrees. So the work, which equals to -1. So the work is going to be -1000 joules, which means that the force of friction is slowing the car down. It makes sense. Another simple example is a man applying a force to a car at an angle of 60 degrees. What's the work done? So here's the man. This time I moved the man to the right side on the car. I don't know what the man can be doing to the car, maybe pulling it with the rope at an angle of 60 degrees. So this is the formula for the work. So F times D, I have cosine between F and D, which is 2000 newtons times 5 meters times cosine 60 degrees, and if I'm not mistaken, it should be 5000 joules. And just note that another formula you may see for work is F parallel. It's a component of the force parallel to the displacement times displacement. So in this case, F parallel is the same as F multiplied by cosine theta. So in this example, we have this cute little pumpkin, child, carrying the bag with candy. So the weight of the bag is 1 Newton and the child is carrying a bag distance 20 meters. How much work has been done on the candy bag by the child? Okay, this is a tricky question. And let's see why it is a tricky question. So the work is the force multiplied by the displacement along, so the force and displacement might be in this one line, okay? So if you use the force times displacement cosine of the angle between them, you can say that the forces of 1 Newton, so basically the child carries the bag with the force of pull, which is equal to the weight of the bag, right? So the bag is not falling down, the child holds the bag. So the force the child applies to the bag is vertical, it's perpendicular to the displacement, right? So the mg is down on the bag, the F pull of the child is up on the bag, right? So, and the child moves to the right 20 meters. So let's see what happens. So we have 1 Newton force, we have 20 meters displacement, but we have the cosine of 90 degrees here. So cosine of 90 degrees equals to 0, therefore we have no work. So it's really weird, but in physics, if the force is perpendicular to the displacement, there is no work that force does to the displacement. I know, that's how it is. Now it's your turn. Please answer this problem on the Google form and pause it now, answer this problem and continue watching this video. So let's talk about kinetic energy. Kinetic energy is the energy of motion, okay? Any point that moves has a kinetic energy. If it has velocity, it has kinetic energy. So this kinetic energy is an energy of one particle. It doesn't have to be consisted of two particles, which is different from the potential energy, gravitational potential energy that we will learn in next video. So this is kinetic energy, and it's equals to 1/2 mv squared. M is the mass and v is the velocity. So let's see. Your turn. Calculate the kinetic energy of this situation and answer your answer in the Google form. Pause the video. So let's talk about work energy theorem. So I can prove this theorem and I will talk about it in class. But for now we just talk about what it is and how to apply it. So the work done by the sum of all forces acting on a particle equals the change in the kinetic energy of the object. And we're talking about motion in straight line, okay? We do not talk about displacements in y direction for the situation, okay? So let's see. In other words, work energy theorem can be written as work equals change of kinetic energy of the object or the system of the objects. Let's look at this example. Mechanic pushes a 2,500 kilogram car from rest to a speed of v, doing 5,000 joules of work in the process. During this time, the car moves 25 meters. Neglecting friction between car road, find the velocity and the horizontal force exerted on the car. Our last example. So here's the mechanic pushing on the car moves to the right with velocity, it's accelerating, we're neglecting any other forces, so we have a net force from the mechanic, which means that there is an acceleration of the car and initial velocity is 0 and the mass of the car is known and even the work of the mechanic is known and displacement is known. So basically, the only thing we want to find is the force that the mechanic is pushing on the car and the velocity of the car at the end of this distance. So let's look at this approach here. For work, we have force times displacement, and we don't really bother about cosine here because it's in the same direction, force and displacement, right? Cosine will be equal to 1, which is 0 degrees, right? So I just put this formula, force from here equals work divided by displacement, which is 200 newtons, if I'm not mistaken. And then when we when we need to find the velocity of the car at the end of the displacement, we want to use the change of kinetic energy. So it's a work energy theorem. So work done by the force that mechanic applies to the car equals the change of kinetic energy of the car. So the change of kinetic energy is always final kinetic energy minus initial kinetic energy. So in here we have final 1/2 mass times V final squared minus 1/2 mass times V initial squared. V initial is 0, so it's only 1/2 mass times V final squared. And if we want to find V final squared, it's going to be 2 times work divided by mass. And if we take a square root of that, we'll get 2 meters per second. Thank you for watching. Please fill out the Google form. Good job.